In a previous video, we looked at boost converter PCB design, looking at the basic working principles of a boost converter, that is stepping up a lower DC input voltage to a higher DC output voltage. You can see this in video number 106 on my channel, and I'll leave a link to this in the description below. In this video, and as promised, I will show you how to size the various components needed in a typical boost converter. That is, we'll look at a specific example with some constraints, choosing the main IC itself, choosing the input-output capacitors, inductor, feedback network, and so on. I'd suggest before continuing on with this video to check out video number 106, again, to familiarize yourself with the boost converter working principle, as we won't be covering this in this video. If you're interested in the same thing except for buck converters, so step-down converters, make sure to check out video number 60 on my channel, which goes over the PCB design and working principles, as well as video number 71, which is the same thing as this video except for buck converter, so component selection and sizing. Thank you to Altium for sponsoring this video. If you'd like to give Altium design a try for yourself, make sure to check out the link in the description below, or go to altium.com/YT/PhilsLab, and you can get yourself an Altium designer free trial, as well as 25% off your first license purchase. Altium keeps adding new cool features to Altium and Altium 365. I'll leave a link to this in the description below, and you can check out all the cool things you can do with Altium 365 and Altium Designer. We saw the boost converter topology in the previous video, that is video number 106 on this channel, and we looked at the basic working principles. In this video, I'll show you how to select the input and output capacitors, inductance and inductor sizing, choose specific parts, the forward diode, as well as the feedback network. Again, for a boost converter, the output voltage will be higher than the input voltage, and we typically get an efficiency of about 80 or more %, because this is a switching converter and not a linear regulator of any kind. Again, for functional description, please see video number 106. What I'll also be showing you, other than these external components, I'll also show you how we can choose a suitable boost converter IC. There are of course many variants possible, and I'm going to just cover the basics, but it should give you a good starting point to look further and for the most common boost converter designs you'll need. Again, we'll need to be choosing C in, C out with inductor L, the forward diode D, the feedback network, and any compensation if we need it, as well as the controller itself, which oftentimes integrates the switch and controls the duty cycle to that switch. Before beginning our design, component sizing and selection, we of course need to define some design goals, and this in turn is dependent on the system we're designing for. A typical application for a boost converter might be for supplying the backlight, power, voltage and current for an LCD display. I've just chosen a fairly random example. This is not application specific, but what we do need to define usually is some sort of input voltage range, an output voltage, maybe an output voltage range, as well as a desired output current. There are of course more specifications and more constraints we can put on our system, but as an absolute basic constraint, this might be it. It's also important to note I've just listed nominal values here. Again, this is just an example of an input voltage of 5 volts, but the input voltage range is important. Do we have minimums, maximums? What kind of deviations can we expect for our input voltage? In our example, I will just be simplifying this using a nominal value, but keep this in mind. The output voltage can of course also be a range, but typically we might be working with a fixed output voltage with an allowed tolerance or allowed voltage ripple. In this case, I'd like to step up my input voltage at 5 volts nominal to an output voltage of 16 volts, and thus requiring a boost converter. We're going to put a fairly beefy current or output current requirement on this, so that this is the output, I out, delivered to the load itself. And we'll see we have various different currents within the design, and this is just one specification of what our load, maybe our LCD backlight, might require at 100 milliamps at 16 volts. The first thing I would then typically do before sorting out component sizing, so inductor, capacitor sizing and so on, is of course finding a suitable boost converter IC. And I'll show you how to do this using a typical distributor part search. When choosing this suitable boost converter, controller, IC, we need to take into account a few different things. Of course, we have to take into account that our input voltage range is suitable, our output voltage range is suitable, it can deliver the maximum output current, plus usually a not entirely insignificant margin, and we'll see later why. We'll also have to choose, for example, switching frequency. Typically, a higher switching frequency means smaller value components, so smaller inductances, smaller input-output capacitors, and so on. But it's a trade-off because it might also have an impact on efficiency, on our EMI signature, and so on. The efficiency, as we said before, is typically around 80+%, especially at higher loads. We have to choose suitable temperature ranges, additional features. Some might include soft start, overcurrent protection, thermal shutdown, and so on. But we might also want to choose the part depending on the required amount of external circuitry. Some boost converters will include the switch, some will include the diode in the form of a switch. Some will require external compensation networks and not just feedback dividers and so on. As you'll see from the distributor part search, which we'll do in just a second, there's a huge selection of boost converters. Additionally, of course, we have to consider cost. The package, is it a BGA? Is it a QFN? Is it an easy to solder SOT23, for example? And of course, the availability. Let's go over to a typical distributor part search now. I'm not affiliated with Mouser, but it's my go-to distributor in any case. On the website, we would of course want to go to power and then power management ICs. And then I would like to go to voltage regulators for the switching kind. Now we have a few different filters and parameters to play with. And remember our specific example, we have an input voltage 5 volts, output voltage 16, output current of 100 milliamps max. So I'll select in stock, of course. I would like an SMD part, and I'd like to choose the topology just being a boost converter. Now we can set our output voltage ranges and so on, of course, but in output current, I'll set to a significant safety margin, so I don't want to be at the limit of 100 milliamps. I'm just going to put this at, for example, half an amp or more. I want one output. We can choose switching frequencies, operating temperatures, and so on. But I'll just leave these filters for now and click Apply Filters, just so we have a broad overview of what kind of parts and prices we can probably see. I'll sort by price, and we already have a few different parts listed here. You can, of course, go into far more detail, specify already switching frequencies, quiescent current, and so on. But let me just open one of these parts. For example, this Diodes Incorporated AP3012. Then I'll open the relevant datasheet. Already on the right-hand side, we can see at the time making this video, it's already a good indication that there are a lot of parts here. Of course, for long term, this doesn't really mean anything. We can see factory lead times and the pricing. So starting at about 46 cents in very low quantities to about 14 cents in higher quantities. The datasheet already tells us quite a few things, of course, on the first page. It's a current mode PWM, constant frequency, boost converter. We can already see the switching frequency is quite high at 1.5 megahertz. And this is typically quite a good thing, as again, it reduces the external components. High efficiency up to about 80%, an output voltage adjustable up to 29 volts, integrated switch up to 500 milliamps, it's got built-in soft start, over voltage protection, and we can use low ESR ceramic output capacitors, that's already a good sign, as we'll see later, and a small inductor. Also the package here is really nice, it's a SOT23.5, it's fairly easy to handle, easy to assemble, easy to test with. But of course not the smallest package you could ever think of, but small enough typically. Pin configurations we can see here, we have a ground, we have a switch node, an input voltage, feedback, and a shutdown signal. Looking at the recommended operating conditions, we can see the input voltage is within range, so minimum 22.6, maximum 16 volts, operating temperatures, and so on. So this seems like a fairly decent starting point given our very, very basic design constraints. Keep in mind, this is rather a simplification. So our choice of IC, the one we just saw, we went through the datasheet, we looked briefly at a distributor part search, and this is how you might begin your search. Of course, you could go directly to a manufacturer that you're familiar with, maybe Texas Instruments, Diodes Incorporated, and scan their website. They often have tools to recommend parts to you, as well as external circuitry. But here are some of the reasons why we might choose this part. Again, the V in, V out limits seem okay. The current limit is with a margin seems okay. High switching frequency, high efficiency, easy package, and fairly inexpensive. And it looks like we don't need very many external components. So this seems like a fairly decent choice to start with. After having chosen at least a seemingly suitable IC, the first thing I typically would do with a boost converter is choose my inductor. This starts off with actually choosing the value of inductance rather than the part itself, but we also have to take into consideration maximum current, saturation currents, DC resistance, package type, and so on. But let's start off with the inductor value. This is kind of a chicken and egg problem because we need to estimate a value of inductor ripple current to give us the inductance, but we actually, in the true equation for inductor ripple current, we need to know the inductance. So typically what we do is first we'll estimate an inductor ripple current, and this is essentially just some percentage of the maximum output current scaled by the ratio of output to input voltage. So this constant is typically anywhere from 0.0 to 0.4 times the maximum output current, so we'll just go with a median value of 0.3. So the inductor ripple current as an estimate is 0.3 times the maximum output current, which is the current to the load, which in our case was set to 100 milliamps by our design requirements. Then we have to multiply that by the ratio of output to input voltage. And again, keep in mind, we're just choosing nominal voltages here. But as you can see, for example, if we lower the input voltage, so if we deviate lower from a nominal, we get an increased inductor ripple. So keep that in mind when calculating your worst cases. I'm just going to use 16 volts for the output and 5 volts for the input, and that gives me an inductor ripple current of just under 100 milliamps, so 96 milliamps. From this and from boost converter equations, we can then solve for the inductance. And the inductance equation is simply the input voltage times the input-output voltage differential, divide that all by the output voltage times the switching frequency Fs, and times the estimated inductor ripple current. Plugging all of these values in, and again, remember you should do this for a worst case, we get about 23 microhenries. We can also see in this equation that the switching frequency f of s, if we increase that, the value of inductance actually goes down. And we can of course see how other parameters such as input, output voltage, and inductor ripple current change the value of inductance we require. 23 microhenries isn't a standard value. The closest standard value is 22 microhenries. So that might be a good choice. However, we should also keep in mind our typical plus minus 20% tolerance of the inductance value. And then again, we should consider a worst case. So a worst case, if we choose 22 microhenries, might be 20 microhenries, which for our situation is probably okay, but you should do thorough checks when designing your power distribution network. Also, when choosing your inductor, of course, we need to be concerned not just with inductance itself and its tolerance, also the maximum allowed current, the saturation current, what package it is, what DC resistance that particular inductor has, and so on. And we'll see that after the next slide. We haven't selected the inductor yet because actually our output current, so our 100 milliamps, which was specified by our design constraints, is not the maximum switch current, it's not the maximum inductor current, and it's not the maximum diode current. Oftentimes, the actual maximum switch, inductor, and diode current is quite a lot larger than the design output current. Let's go through an example here. First of all, we need to calculate the duty cycle. So effectively, how much of the time is the switch on compared to how much of the time is the switch off. And for a boost converter with a certain efficiency, the Greek symbol eta in this case is about 81%, and we can get that from the datasheet. The duty cycle is then 1 minus the ratio of input to output voltage times the efficiency, which gives us about 75% duty cycle, or 0.75. On the next line, we can then see the actual equation for inductor ripple current. Remember, the previous slide only showed an estimate for us to choose appropriate or approximate inductor value. We can see the actual inductor ripple current equation includes the inductance, and that's why we had to calculate the inductor value first. Plugging in all of the values we have here with our switching frequency of 1.5 megahertz, inductance, input voltage, and duty cycle, we get an actual inductor ripple current of about 110 milliamps, so actually not too far off our 96 milliamp estimate we had before. Using this inductor ripple current, dividing this by 2, adding our output current and dividing the output current by 1 minus the duty cycle, we actually get our maximum switch, inductor, and diode current, which is quite significant at 460 milliamps. Compare that to our design or load output current of 100 milliamps, that is quite a difference. So we need to ensure that the switch, inductor, and diode are rated to this peak current, and of course we should add some margin on top of that. This is also to show that despite us having a 100 milliamp output current requirement, it's good that we chose a part, our boost controller, that has a 500 milliamp switch inside of it, so it's rated to this peak current we can expect. With this information of maximum switch, inductor, and diode current, as well as the information of requiring about a 22 microhenry inductor, we can now choose a suitable part. So back at Mouser or your preferred distributor, I'll go to Products, Passive Components, and Inductors. Then I would like to choose Power Inductors and SMD. So in the power inductor section, I've selected my inductance, which was 22 microhenries, as we saw from the previous calculation. Remember, this is nominal, we'll have some tolerance, and I've chosen a shielded inductor just to start with. Now we have all of these other parameters also available here. For example, the tolerance, maximum DC current, maximum DC resistance or DCR, saturation current, operating temperatures, and so on. Importantly for us, of course, you want to choose an appropriate maximum DC current. Our inductor has to sustain about 450 to 500 milliamps, but we'd like to add some sort of safety margin as our calculations are pretty much all approximations. Therefore, instead of choosing a 500 milliamp inductor, I will probably go with 50% more than that, so 750 milliamps at least. And also our saturation current should have at least that rating as well. Tolerance, I'd like to have 20% or below. When it comes to DC resistance, of course, the lower is typically better unless you have particular requirements, because this will improve the efficiency of the conversion. By sort by price, we have various different choices. You can see here we also have not recommended for new designs, so I definitely wouldn't pick one of those unless I have no alternative. But for example, one of these first parts here, let's have a look at this one by TDK, about 40 cents per part. It's fairly small, 5mm by 5mm, maximum DC current of 1.8, so that's very much sufficient, saturation current of 2 amps, and a fairly okay DC resistance at 125 milliohms. Ideally lower, of course, but as a ballpark figure, something around 100 milliohms or less is usually okay in most applications. So we might go with some part like this. You can see there's quite a lot more than to just an inductance value. We need to consider packaging, shielding, inductance, tolerance, DC current, saturation current, DC resistance, and so on. In a typical boost topology where we have an external diode, so it's not internal to the controller or the boost IC, and isn't, for example, a controlled switch as well, we'll have to choose our part as well. This diode should be a Schottky diode, Schottky having a lower forward voltage on average to reduce losses. Our forward current rating should also have a minimum of what our maximum switch inductor diode rating was, so we saw that was about 460 amps, and that should be the absolute minimum rating of our external Schottky diode. The power dissipation, of course, needs to be considered, power being the forward voltage of our diode times our maximum forward current. So in this case, about 0.5 amp times whatever forward voltage we have. We will, of course, need to consider package size, the cost, availability, and so forth. So back on Mouser, going to the discrete semiconductors and Schottky diode section, we can do our usual procedure, seeing what's in stock, the mounting style, package case. Our forward current, of course, should be greater than 500 milliamps. And again, we can put some safety margin on that, so at least 750 milliamps. We have various other parameters, such as repetitive reverse voltage, of course, has to be suitable for our input-output voltage differential. So that needs to be chosen appropriately. Our forward voltage should be small enough, again, so we reduce losses and our VI losses as well. So a potentially suitable part, even though maybe a tiny bit pricey, might be this SKM14. Fairly small package, 1 amp forward current, large repetitive reverse voltage, fairly low forward voltage, but of course this is just skimming over it. There are different types of switching converter ICs, some which have a fixed output voltage and you don't need some sort of external feedback network, but typically you will have an external feedback network, meaning you can set the desired output voltage. The feedback network typically is simply a resistor divider, but your datasheet of the chosen part of the chosen controller will tell you more about this. It's incredibly important to follow the datasheet recommendations, and we'll see that in just a second. Again, the minimal is just a resistor divider, as we see on the bottom right-hand side. So RFB1 and RFB2, which essentially scales down the voltage of the output to after the output capacitor and feeds it back into the controller. So the controller has a negative feedback path to adjust the duty cycle, to adjust for any load variations and so on. Sometimes we do require additional compensation, so you might have some sort of parallel capacitor to one of these feedback dividers. The controller itself might have an additional compensation pin, and all of this will be detailed in the datasheet. Depending on your constraints, it's oftentimes simpler to just choose a controller which doesn't require external compensation. Again, this is design dependent. Also, the magnitude of the feedback resistors is important. This could be for power draw. For example, in low power designs, you might want to scale up the feedback resistor dividers. However, large dividers, larger magnitudes of resistors might introduce more noise into the feedback loop. Resistor tolerance is important. Typically, we would like to go with 1% tolerance resistors, unless you don't have a particularly tight voltage constraint of the output. Also, the internal controller voltage reference, so it'll compare this feedback voltage to an internal reference that will have some sort of variations, and for very tightly constrained systems, this will be important as well. From the datasheet of our AP3012, I took this equation, which is the output voltage is 1.25 volts, and 1.25 volts is this controller's voltage reference, and that will change depending on the part you choose, times 1 plus the top feedback resistor divided by the bottom feedback resistor. And this equation you'll pretty much see in every design, the only change being what reference voltage this is. As we did with the inductance, is also for the resistors incredibly important to choose standard values, unless, again, you have very specific constraints or requirements. This is simply to keep the cost down. So if you calculate that you need a 22.1K resistor, go with a 22K resistor, for example. Going to the datasheet of our AP3012, looking at a typical application circuit, we can also see at the bottom here, this is where this feedback divider equation comes from. It's also listed elsewhere in the datasheet. And we can also see this typical application doesn't require external compensation. We just need R1 and R2 taken at the output voltage node. And we have these magnitudes of these resistors. So this already gives us a good indication. We shouldn't be using mega ohms. We shouldn't be using hundreds of kilo ohms. We should be using around tens of kilo ohms in terms of magnitude. So 5K1 is a standard value, so I'd probably stay with R2 being 5K1 and simply adjust R1 using the Vout equation to get myself 16 volts. For our very simple boost converter design, we've almost selected all parts required, except of course for the input and output capacitors. I've left this for last as this is probably the most involved part and sometimes a bit vague and ambiguous, and you have to choose ballpark values or simply just rely on the datasheet recommendations. For boost converters, typically they'll be happy to use input and output capacitors that are ceramic. Typically, these will be class 2 multilayer ceramic capacitors, which are prone to derating, be this if it's an applied DC bias voltage, if it's temperature, and so on. So if our input voltage is 5 volts, and we choose an input capacitor of maybe 10 microfarads with a 10 volt rating, it doesn't mean we'll actually have 10 microfarads once we have this 5 volt input voltage applied. We'll probably have a much lower input capacitance due to derating. To have a look at how typical MLCC class 2 capacitors derate, I'd highly suggest checking out this free Murata tool called Sim Surfing. I've got this open right here. You can search for different capacitances, rated voltages, actually find real world parts and look at their characteristics. I've chosen this 10 microfarad, 10 volt X7R capacitor in an 0805 package and opened the capacitance versus DC bias. So at 0 volts DC bias, we can see I have a capacitance of about 10, slightly above microfarad nominal, but once we apply 5 volts DC bias to this, so around here, this capacitance has pretty much halved down to 5 microfarads. So this is incredibly important to take into account. Of course, we also have this derating effect also for temperature. So for example, at 0 degrees compared to 80 degrees, we'll have a different capacitance as well. So this is something we really need to take into account. We also sometimes have the choice between ceramic, tantalum, or electrolytic capacitors, although most boost converters running at high frequencies are specifically designed for low ESR ceramic capacitors. You should pay attention to the datasheet. We need to pay attention to ESR, so the series resistance, equivalent series inductance, the dielectric type, derating depending on temperature, DC bias, and so on, maximum capacitances you can get in packages, and so forth. This will have an impact on the voltage ripple, on stability, frequency response, and so on. You can see this is quite a large topic and definitely too big for this video, but I'd like to give you the basics and some things to watch out for. Importantly, if you follow the datasheet recommendations and their calculations, you'll usually be fine. A guideline might be for internally compensated controllers, such as the AP3012 we are seeing in this video. The guideline is that if they give you a recommendation, for example, a certain type of inductance and an output capacitance in a typical application example, then that should be constant. So if you need to increase your inductance, decrease the output capacitance and vice versa. So here in their typical application, we have L1 at 10 microhenries and that output capacitance at 1 microfarad. So 10 micro times 1 micro should be constant. That's a very approximate guideline, keep in mind. The input capacitors typically will be low ESR and they have to be able to supply the peak currents. Again, follow the datasheet recommendations. We'll see this in just a second. The output capacitors, as a general rule of thumb, the higher they are, so the more capacitance you have the output, that will typically lower the output voltage ripple. Again, it depends on if the device is externally compensated or internally. We might have stability problems if we go too high or too low. If we're not given any value in the datasheet, which is rather unlikely, for low ESR caps, so we don't have very much series resistance for output capacitors, this is typical for modern ceramic capacitors, our minimum output capacitance can be estimated using this formula. So in our example with a 100 milliamp output current, our duty cycle of 0.75, 1.5 megahertz switching frequency, and a design output voltage ripple of 10 millivolts, we need a minimum of 5 microfarads. If we're allowed 50 millivolts output ripple, this output capacitance minimum drops to 1 microfarad. And this is also in typical application, we can see we have very small input-output capacitors, and these are ceramic types. We can see they have certain dielectric recommendations and so on. The actual datasheet for this AP3012 doesn't tell us very much about the input-output capacitors other than the recommended application note we see here with our input and output capacitors of 1 microfarad. So there's not very much help, and you have to rely on this constant L1 times C2 parameter or size it on the equations we just saw. Typically with other manufacturers, you'll see maybe slightly more involved datasheets. This is typically true for Texas Instruments. And this is a far more involved boost converter with a higher output current limit, with external compensation, soft starts, and so on. And they will give you all the equations you need to design for this particular boost converter, including a typical application, typical values, and the equations they used for this. I hope this gave you a good overview of where to look and what to take into account when sizing the external components and also choosing the boost converter IC itself. Typically, the datasheet should contain all information, but along with this video, you should be able to perform some of these calculations yourself if the datasheet is missing these calculations or recommended values. Again, please check out video number 106 on my channel if you'd like to see how to lay out a PCB and route that for a typical boost converter. And if you like the video, please do leave a like, a comment if you have any questions, and don't forget to subscribe to stay up to date with any DSP, hardware design, and PCB design videos. Thanks again for watching, and I hope to see you in the next one. Bye bye.